All right, so
Oh, Stephen, do you want to hit record?
okay, so today I am pleased to introduce Cassie Lumbrazo, who joined UW in fall 2018. She got her master's degree in summer 2020, studying forest-snow interactions. And then she spent half a year in Switzerland and then 9 months in Norway, managing to escape the US during the majority of the pandemic. And now came back and is going to be discussing the work she conducted there and in Washington State, and giving her plan for her PhD.
Awesome. Thanks, Jessica. Yeah, thanks everybody for being here and everybody that's online as well. I hope you can hear me. If there's any issues, you can comment in the chat about it. Yeah, so this is my general exam presentation. So for people online, like my mom, who may not know, the general exam, the goal is to basically give a proposal of the rest of my PhD. So I'm going to talk to you about some of the work I've already done, and then, yeah, some of the work that's taking place and that I'm going to be completing this year. So if my slides would advance, then we could get started. Okay, so this is a really big outline of what's happening, but I want to simplify it for you. Well, first, I should probably give you my title, actually. Is investigating forest-snow interactions to inform global modeling and forest management. So there's kind of two pieces here. There's the global modeling perspective, and then there's the forest management perspective. So this is the big outline, but I want to just focus in on investigating the forest-snow interactions from two different perspectives. So we're going to start with that global modeling perspective, and I'm just going to give some overview on why you should care about forest-snow work. So when you're out walking in the forest, it might look something beautiful like this in the Pacific Northwest with our beautiful coniferous trees. And we really like to show this to highlight forest-snow interactions. So it's a really complicated, there's a lot of complicated processes happening here in just this video and when we are out there. This is in the Olympics in Washington State. I guess, you know, the goal here is to give everybody an idea of really how much our forest can impact our snow. So a few things can happen. You can have, you know, our snow be intercepted by the trees, which you can see here. You can have that snow unloading onto the ground below, which you also see when the trees are breathing. And then you can see towards the end of the video, as you get into April, May, it actually impacts the ablation period. So you can see as the snow is melting, that it's melting in different ways if you're in the gap or underneath the forest. And also you just get a beautiful view of the Olympics here. This is Mount Hopper. And this is a video created by Ryan Currier. So yeah, you get to see the full melt out there, which is pretty cool. Okay, well, if I'm talking about, you know, I'm a snow hydrologist, and now I'm talking about trees, and you're like, Cassie, what are you saying? Well, where snow matters for water resources, this region really overlaps with trees. So this is like these cross hatches are where there are forested areas and snow. So this is not just in Washington State or in, you know, in just North America. This is this is a global idea, and also in the Northern Hemisphere, we can really focus in on where snow matters for water resources, really, those areas overlap with trees. So back to my tree photo here. This is not just actually any photo, it's a time-lapse image. So if you guys have heard of my work before, I've used time-lapse photography a lot. This is a photo from Switzerland. And what we do with time-lapse photos is we can actually get observations of these really complex processes. So of course, it's quite limited, but we get photos every hour or even finer scale resolution of what's happening in the forest. And this is way more information than you can normally get if you're just out there for a day or 2 or 3. You can get a whole year or 5 years worth of information about forest snow processes. So I'm going to introduce all this with my first paper from my master's work that's already published. So bear with me as I explain to you how that leads into the first chapter of my PhD. So like I said, we are using time-lapse photography to really get these observations of forest snow processes. And this is just, love to highlight this work. This wasn't started by me, but we were able to take those time-lapse images, upload them to a citizen science platform. In this case, it was Zooniverse, and we were able to get all of our images classified for the presence of snow in the canopy. So this was a simple binary classification by a citizen scientist of these images. And it was hugely successful. It was a really cool project. People loved looking at these photos. There's 9,000 volunteers and 20,000 images more now classified. And we have undergraduates that have helped us on this work. And it's a really great learning mechanism for many people. But I wanted to do something with this data because there was a lot of data. And so what we did was take those classifications of presence of snow or absence of snow, and we were able to use that to evaluate hydrologic models. So we were able to say, if our model was modeling snow in the canopy, then at the same time as our observations of snow in the canopy, then we're getting that time step correct. So simple binary. I used 3 models, which I'm not going to go into the details here. You can reference my paper if you want. But I want to explain to you what the difference of these models are and what we saw. So this is big figure going on here, but what you have up here is snow in the canopy being modeled by all of our different models, whether or not they were calibrated or not. And then you have some wind speed and temperature and precipitation to give you information about what's happening. And I just want to highlight, so what we saw a lot was some errors actually in the interception part of the modeling. So we saw that for A, B, and C, that we were modeling interception events that didn't exist. But we also had errors in the unloading. So this is the piece that I was focusing on for the work, is our unloading model. So we had 3 different models that were either calibrated or not, and some of them would capture these events, and some of them would actually have snow in the canopy for an extra day or 2. This is an example where A, B, and C are for the same site. This is Niwot Ridge in Colorado. And for A, B, and C, actually, a few of the models captured the event properly, but not necessarily for the right reasons. The exponential decay is capturing it properly, but it's just an estimate. And you can see later on that all the models actually end up with more errors too. So this was a complicated kind of problem to unravel. But essentially, we kept seeing this idea that the error in snow in the canopy that we were seeing in our models was often when the temperature was less than 0, because a lot of the models are only considering temperature less than 0 snow unloads, or even simpler, just an exponential decay. This is another site just to show you in a different climate. The opposite was happening in that our temperature was a little bit below 0 maybe, or a little bit above 0, or right at freezing, and snow was unloading, but we actually didn't have all the snow unloading. That's the Matt Hopper video that you saw. So this is a complicated problem, but we tried to essentially summarize this into saying that our models aren't capturing everything, but some of them, if they're calibrated locally, do a pretty good job. But really the issue here is that we don't have global calibration data. So we don't really know everywhere exactly what parameter values you should be using. So this got us curious. What we started looking at was actually what physics are missing in our models that we can include so that you don't have to calibrate locally, so that our models can be more transferable. And of course, because I didn't get enough of looking at time-lapse images, I was like, well, what other information can we get from our images? So this is where it led me into chapter 1, where I'm going to be talking about kind of a follow-up of this work. And this is in collaboration with, this work really started when I joined Jessica at SLF in Davos, Switzerland. So I'm going to be talking about their field site and then show how we expanded from there. So like I said, we're here now, we're in Davos in Switzerland, and we did a forest snow field campaign here. This was a really excellent experience. It was my first time having very intensive observations happening in the forest with a lot of different people that had a ton of knowledge. So this is Julia digging out one of our local Met stations. We had small Met stations throughout the forest, and we were mostly focusing on forest snow interactions, of course. We want to expand these observations. So we had actually sites like this where we had cameras on either side of a shaded or a sunlit side of gaps. So what we were able to really do here was start looking at how other variables, when temperature is less than 0, are impacting snow unloading. And what we really saw here, and you can even see it in this image at the start, snow is starting to unload when sun is hitting the canopy. We can kind of say when shortwave increases, depending on where your sensor is, but we were really observing this when we're standing out in the forest. Like we see the snow starting to unload from that south aspect. So we started investigating this more. So I started asking what other information can I get from time-lapse images. And I'm going to walk you guys through this. This is air temperature over time. And I am kind of filling in the space of the observations here. So I'll walk you through what those are. So then if we were to expand this into other meteorological variables, such as shortwave and wind speed, and we can start with a classification here, which is, this is no observations of, so it's overnight. Obviously, we're limited to daytime. So this is an example of no observations. This is an example of no snow in the canopy. That's what that looks like. And anything that's colored was when there was snow in the canopy. And then so that was our previous data set, was just snow in the canopy or not from citizen scientists. But what I did was spend a lot of time looking at images to create these data sets where we got more than just snow in the canopy. So what we did was, once we saw from the citizen scientists saying, yeah, there's snow in the canopy, I went and looked at those events. And I said, okay, if one time step to the next had a decrease in the amount of snow for whatever reason, for many reasons, then snow is actively unloading for that time step. And I also made some other observations from the images, such as if the canopy was sunlit. And then there's this color of where that overlaps, because when I was doing investigative analysis, we really wanted to just see what was going on with the meteorological data in collaboration with the time-lapse image information. So what we can do, the power of this, is then we can actually step through time and start looking at our time series. We have our observations of snow in the canopy throughout time, and we can look at the meteorological data and see what is happening in the meteorological data that is causing snow to unload at these time steps. So if you can imagine, I spent a lot of time looking at plots like this. And we're really like thinking back to this type of event and thinking, okay, well, if we're observing this increase in shortwave and the sunlit canopy, snow's unloading, we're really trying to be like, okay, well, can we see this in the meteorological data in some way that can improve our models? So this is Lorette, that's that same field site. And I just want to highlight an example. So we have a Met station in the forest, Met station in the open. And the other one is a larger Met station nearby. So we have the same observations for an event. And if you look at March 19th of 2021, you can see that we actually have snow melting out of the canopy when the air temperature is less than 0. That's exactly what we felt when we were standing out there, of course. But you can actually see it in the meteorological data. And you can see that in the air temperature is in fact less than 0. It's approaching 0 as a maximum in the day, but we had an increase in shortwave. And so this overlaps with our sunlit canopy observations and snow starting to unload. And essentially, we're able to summarize all these observations, looking at all these unloading events, and see these relationships between snow staying in the canopy and snow unloading. And the really cool thing about Lorette was that the difference in the means between temperature and shortwave for snow staying versus snow unloading were statistically significant. So we had large differences in the means for those being predictors for unloading. However, wind speed at this site there was not a large difference in the means. And this is a really kind of protected site, not strong wind speeds there. We never experienced that standing out in the field. So that made sense to us. And so what is really helpful here is that we can actually look at the relationship between air temperature and shortwave without the interactions of wind speed at this site. You can imagine that I wasn't done here. So then I was lucky enough to take the VALA program. It's a Scandinavian exchange program. I visited Claire Webster at the University of Oslo in Norway, and she was an incredible mentor and even brought me on a field campaign at Sodankylä in Finland. So I had previously looked at time-lapse images from this tower for previous work with the first chapter of the work, with the master's work. And then I actually, because of these folks, was able to go stand underneath that tower. So it was a really excellent experience to understand what was happening at Sodankylä. Of course, a lot of other things happened at this field campaign, and I hope at some point we can share a lot more about that. It was really awesome efforts from these folks, and these are my collaborators in the top from SLF that I started this work with in Davos. So when we're talking about Sodankylä, I just want to show one example. I'm not going to bring you through all the images the way I had to, but one example is this is super common. We have no shortwave at Sodankylä. It's in the Arctic, northern part of Finland. In midwinter, we don't have to think about shortwave. But we can look at air temperature over time, and wind speed. And we have this unloading event here where snow started to unload, and you can just see in the metadata that spike in wind speed. It's obvious with your eye. But of course, you can also look at the images and you can physically see the trees shaking the snow out of them. So these types of observations, I just think were really interesting to look at. So I didn't stop there, of course. Well, we went back to Niwot Ridge that I started with earlier, and we did the same thing. So I looked at the unloading, and so we were able to compare all three of these sites. So this is snow unloading versus snow staying with all of our sites. So what I just want to highlight here is that at Seduncula, like I said, we have very small amount of shortwave in the winter. So we were able to actually look at the impacts of air temperature and wind speed. At Niwot Ridge, we actually have all three of these variables interacting. So it was a great opportunity to compare what we were seeing there with all three variables interacting. It's fairly complex to like kind of piece these things apart, but we tried our best. And essentially I came up with some summary results here is that we showed that we really must consider the interactions between meteorological variables if we want more transferable models. So when air temperature is above 0, we can leave it at that maybe for modeling. But if it's below 0, we should really consider these interactions to improve our models, right? We're seeing it in the data. So one idea is that if air temperature was actually below -3, so it was really cold, then we saw that pretty low wind speeds could unload snow. This is not a new idea. The cohesivity of snow actually changes with temperature, but this is not included in unloading models. And shortwave radiation, of course. We saw when the shortwave radiation in the metadata was above 400 watts per meter squared, then we were able to see unloading, especially after it was that high for over an hour. And this is, of course, also well known that shortwave will heat the canopy elements, but it's also not included in models. So this is a majority of our hydrologic models and what they actually do include. And you can see most of them will just use temperature as a predictor. Some will include wind, and almost none. One includes shortwave. So if we want to improve our modeling, then we should probably be considering these things. I'm going to go through this rather quickly, but we did some test modeling because we were just curious. We kind of built on that first paper where we took a parameterization that already included temperature and wind, and we added shortwave. And we were able to test also the impact of air temperature on wind speed. So we kind of added a correlation there based on our observations, and we added a simple shortwave parameterization. So a short overview of this is that this is a similar plot to those first published plots, where we're looking at an example of kind of this threshold working for snow being stickier at these temperature values. So we have a low shortwave, a low temperature, and we have wind speeds that can unload snow at fairly low values. So you can see there's a decrease in our plot. In the black is our model that we're calling shortwave wind temperature. But of course, I looked at a lot of this, and we can see events like this, which are really interesting, where we had observations of the canopy being sunlit, and then snow started unloading, and our model in black does have that decrease in unloading. And you can see it actually does kind of follow this exponential unloading model, which is just an estimate, but then has a spike again. It must have started snowing again, of course, the model started accumulating, but we actually captured this unloading event there. So I don't want to spend too much time there because I mostly want to give you guys a wrap up of what all this means. So in chapter 1, this is all that unloading work I was just discussing. We actually just compared all these models and we said, okay, are we getting the timing of snow in the canopy correct, which is just presence or absence of snow? It actually performed fairly similarly to the other models, the shortwave wind temperature, but where it excelled was capturing the time steps that the model was unloading. So like you can see in that figure I showed is that those small unloading events were continuously being captured because we included the meteorological data. Okay, so a summary of this is that we created a data set that can be widely used. It's 3 sites from very different climates that has a lot of information. So this is available, people can use it. And small adaptations to existing models can improve their performance if we include these interactions between meteorological variables. to improve the timing of unloading and reduce the need for site-specific calibration. Okay, so there's the snow unloading world as far as the perspective of global modeling goes. And that first paper is published, and for my chapter 1, this is a manuscript that all the analysis is complete that I just showed you, and I'm writing. And I want to switch perspectives now. So I want to move to the perspective of investigating forest-snow interactions, but from the perspective of informing forest management in Washington State. Well, we can't think about forest management in Washington State without thinking about fires. So this is just an image of fires in over the North America. And you can see tons of smoke inundating the US. And if anybody was here last fall, the Bull Creek Fire and Cedar Creek Fire caused smoke to come over Seattle, Washington, and Portland. And so these events, these large fire events are happening, and they're not happening without a response from us. So forest management is currently happening out in our forests to try to reduce our risk of these large severity wildfires. A lot of these forest management techniques are either logging, thinning to reduce the fuels in the forest, or different methods of actually having prescribed burns to reduce the fuels in the forest. And this is all from the perspective of increasing fire resiliency. Of course, we want to reduce our high severity crown fires. But that's not the only thing that we're managing forests for necessarily. So I want to make sure I do mention there's a whole view of things that we manage forests for. It's to have healthier forests, to have increased wildlife habitat, to have watering streams for fish at the right times. Of course, there's monetary value component. This needs to be funded. This sustainable forest management needs to be funded. And we want to also increase our recreational areas because we all love being out in the forest. And then the piece that, of course, I'm a snow hydrologist. You're like, Cassie, you're talking about forest again. Well, I am talking about forest because I want to make sure that we are considering water resources when we're talking about doing these forest management. So what we want to consider is we want to ensure that there is appropriate stream flow for fish, and we want to ensure that there's enough water for agriculture and other uses downstream. And when we're talking about fire resiliency and this water resources question, the big overarching question of this perspective is, do these forest prescriptions for fire resiliency also promote hydrologic resiliency? So we're interested to say, okay, if we're already doing this management, we want to make sure that we're not depleting our water supplies at the same time. So that's kind of the overarching work of this. So I'm going to move into the field site and tell you about the site that we're working at and some of the work that's going on there to try to answer this question eventually. So this is a TNC in Washington DNR. This is in collaboration with them and funded through them. So want to make sure I highlight that. So this field site, we are working with the Nature Conservancy, and they're very motivated to do selective thinning projects for these reasons, to reduce wildfire risk and create healthier forests. This is an article published on the work. Actually, this work is not yet peer reviewed fully, so we're kind of working off preliminary news articles. So the Nature Conservancy purchased 38,000 acres in the Central Cascades that was actually going to be sold for development. And their goal was to restore these forests and also do some testing of how these forest management practices impact other mechanisms. So we're going to focus on a 340 acre forest. It's just north of Cle Elum. And this is part of that larger purchase, but there was an experimental forest design happening here that I'm going to tell you guys about. And so this is that zone that I'm going to zone in on, and this kind of outline is the outline of our region that I'm going to use throughout the next slides. So if you're looking at, if you're standing in Cle Elum and you're looking, up at the ridge, it's just directly north of Cle Elum on the east side of the Cascades, and you can see, it's a beautiful view up there. You can see Mount Stewart and sometimes Glacier Peak. That's a pretty far view, but on a clear day. But this is a photo from Mark Stone, who has joined us out in the field a few times. It's just a beautiful photo of being up on the ridge. So this is what it looks like up there in this 340-acre forest that we are looking at. Okay, so here it is, again, on a map, and I want to give you an idea of where it exists in the world of hydrology. So this is the Yakima River Basin. So we are in this northern plot of the Yakima River Basin. And the Yakima River is, this Cle Elum Ridge, I'm not sure if I said it yet, but the field site is called Cle Elum Ridge. And it's at the headwaters of this Yakima River. And of course, the Yakima River is the largest river entirely within Washington state. And all the water is stored in 5 small reservoirs. And the irrigated, all that water from reservoirs gets dumped into our lowlands to support irrigation for a lot of different crops and productive agriculture. It's a very productive region for agriculture, and actually it's 75% of the US hops and up to 70% of Washington state cherries in this area. So if you care about beer and cherries, then you might want to know, I'm looking at you, Joel. Then you might want to care about the water resources in this region. But when I'm talking about that, what does it actually mean? Well, I'm a snow hydrologist, so 75% of the runoff from this basin comes from snowmelt in the spring. So if we want to have our cherries and have our hops and make sure we have our fresh water later in the season for fish and streams, we want to make sure we are looking at snow. So if we're looking at snow depth over time, we have a snow accumulation in the winter, and then we have it melt out later to supply to our reservoirs. And for a million reasons, you could have snow end up decreasing, and this will cause less accumulation and really that earlier snow melt. So if we want to make sure we have all that water available, what we want to do is really maximize how much snow we're keeping in the forest and how long we're keeping it for. And really a beautiful thing of this is that our snowpack is a natural reservoir. So it's a reservoir sitting up there at the higher elevations of this river basin, and it's holding our water for us. So if we have smaller reservoirs in the Yakima River, then this is just going to help out regardless for hydrology to keep snow longer up in the mountains. So for talking about snow, we can't talk about it without talking about forest. So a lot of these areas where snow is also overlap with forests in the Yakima River Basin. 40% of it is forested, and most of that is where the snow is. And a lot of the other land is actually used for productive reasons. So it's a really interesting location. And I want to talk about forest-snow interactions by talking about Jessica's 2013 paper here to talk about essentially how these two variables are going to interact at this field site. So whether or not snow lasts longer in the clearings versus under the forest is actually strongly dependent on temperature. So Jessica's 2013 paper, this is just a summary note of if we're in warmer regions with warmer winters, then the trees are going to melt the snow. And if we're in regions with colder winters, then the trees are going to shade the snow. So you'll have snow last longer in the forest. And it's actually really interesting how these processes work because in our area, because if you look at this temperature plot of the winter, so December, January, February average temperature, our Yakima River Basin the northern part is actually sitting on this verging temperature zone where our temperature is sitting not necessarily in either one of these categories. We are kind of teetering on this warmer winter, the colder winter, and we're not quite sure how forests are going to impact snow retention in this area. And if you were to transcribe the temperature into snow lasting longer and snow staying longer in the openings versus the forest, it kind of is split in the Cascades, of course, where you have snow lasting longer potentially in the forest as a hypothesis, but it's likely to change if temperatures are changing, especially in the winter. So that's really that zone that we're zoning in on. And previous work by Jessica and a lot of other folks have looked at these interactions, but we're really looking at this region that is quite uncertain for how forests are going to impact snow. So that's the overview of the perspective from Washington State. And I want to now tell you guys about how I'm going to build 2 chapters out of this and where this work is going. So this is just examples of our really dense forests before any forest prescriptions take place. So we have a lot of dense forest and some amount of snow accumulation in the forest. And the first part of this work is chapter 2, is we're going to look at the pre-treatment for snow situation. And this work is funded by Washington DNR. We want to create a baseline analysis for how the pre-treatment forest snow relationships interact. So we want to develop a predictive relationship between snow depth, forest density, slope, aspect for our pre-treatment forest structure. So first we need to understand, before we do anything in the forest, what is the situation? And then we can look at, if we change the forest, what happens later. So we're starting here. And I was lucky enough to get a proposal funded to get the first ever LiDAR data flown over this, snow on LiDAR data flown over this region. So we're going to use this LiDAR data set to tell us more about what happened, what's happening in the forest before we do any prescriptions. So this first snow on LiDAR data for the region was flown on April 1st of 2021 by NCOM. And we have a base snow off LiDAR from Washington DNR from 2018. And now we have a snow on. It's the first ever for this region, and LiDAR data is very useful. And I'm going to just do a small overview for those that may not know what LiDAR data is. So LiDAR is light detection and ranging. It's commonly known as laser radar or laser scanning. You might hear people just saying lasers. But essentially, it can be confusing. But essentially, you can think about it as this laser that comes, of course, comes out of the plane or whatever it's mounted on. It can be on a drone or on a constant object. But essentially, it's coming down, and you can see that there's a return off the ground, and it's going back. And this tells you something about where that return came from and what that distance is. So if you have something that's not fixed, like a point on the ground, you can have these structures that maybe aren't staying completely uniform, and you can actually end up with a bunch of returns in the forest canopy, including below it. So we can get returns for what the snow depth is under the canopy, for what the canopy height is, and even get information about the canopy structure from this data. And you end up with this 3D point cloud people talk about, which are really cool to look at, but take a lot of processing power. And essentially, this is what you'll start with. And you can get this detailed forest structure from the LiDAR data. And this is really the power of this work, is that then you can see what that also means for what's underneath the forest, because you can actually get returns below. So for our field site, I'm using the LiDAR data that was collected. It's NCOM snow on LiDAR data. And we want to develop a predictive relationship between snow depth, forest density, slope, and aspect for our pre-treatment forest structure. So remembering where we exist in the world, in Cle Elum Ridge, just north of Cle Elum. This is an example of that LiDAR data. If you zoom in, over our ridge, there's the outline of our forest treatments. This is slope. So one thing we can get from LiDAR data. We can also get our forest density. This is a canopy height model from the LiDAR data, which can give you that canopy structure information that is highly valuable for our work. And then you can get things like aspect. And this is a really, I want to focus on this for a moment here, because aspect on this ridge is really something very valuable. So you can see there's north aspect in red and the blue aspects in south and southwest. And this ridge really is east-west running. So we have this like almost perfect comparison between this north aspect and south aspect right on the ridge. So from a south aspect, this is a photo from Susan's paper in review. From the south aspect, you have something like this that exists. And then on the north aspect, on the same day at the same time, it can look completely different. So when we want to understand snow and forest interactions at the site, we really want to know, we really want to focus on aspect and canopy structure. And really, this just provides a perfect opportunity, especially because a lot of forest management is interested to happen on the south aspects, because there's increased chance of fires and they want to reduce fuels over there. But we want to make sure that those management practices are also promoting hydrologic resiliency. Okay, so I gave you a little bit of an overview of this work. And This is chapter 2, which is currently in analysis. It's funded by Washington DNR. And our goal here is to produce a technical report that is going to be highly valuable to Washington DNR to understand what was happening on this forest before anyone started doing any prescriptions. So now I was talking about forestry work happening. You're like, you haven't told me about what the forestry work is, Cassie. So here is chapter 3. We're going to look at the post-prescription forest snow analysis. So this work is in collaboration with Emily Howie and Susan Dickinson-Lang and Jessica. This is funded by Washington DNR and TNC. And we're really interested to now then move into understanding the post-treatment forest snow. So we have our pre-treatment structure. And then if our forest structure changes, this is also going to impact the snow, of course. It seems pretty simple. What we have here is our treatments up in the forest now on top of our plot. So if we go and look at them and we take a look from, that's not the right slide. Okay, so if we look at our forest treatments, they're in kind of this range of basal area factors, which is essentially, we can try to relate it to forest density, but it's essentially this amount of basal area in an immediate region for the site. So these treatments were done very strategically with a tremendous effort from many people. This photo of Herman from TNC and Remus and Emily Howie and Augie and many other people worked really hard in the forest to make sure these treatments happen. What they did was, the goal was to keep the older trees and the most fire resilient trees. And this means keeping ponderosa pine and removing more flammable species. And I mean, I can't emphasize enough how much work went into this. People were out marking individual trees for loggers to cut. So, I mean, it was just a huge effort from many people to make sure this prescription happens. I think, this project's not funded by like one big NASA grant for 5 years. This is collaboratively worked on because people love this stuff and just want to really see this project through. So Emily and Herman were able to communicate with the local logger. Really, the local logger, like he is the one who was doing all the logging by himself up there on the bridge to make sure these treatments happened. This is just really interesting. If you've ever been in the Portland airport, our trees from this field site are they're partially creating the roofing lattice of the Portland airport. So yeah, I mean, it's really cool. I don't know if Rob is embarrassed or proud, but I'm pretty sure there's a photo of him like printed on the wall, like a massive photo. So if anyone goes to the Portland airport, you can take a photo for me of the ceiling and also of the photo of Rob. So, and they even highlight our field site on their website. So the goal is to really support sustainable forest management. And so, this work is spreading further than just our little ridge. So if we look at our forest treatments from the top down, then we can see that they're pretty spread out. These are like estimates of the forest treatment zones on the ridge. And it's just increasing in basal area factor. You don't have to worry about it too much yet, because I'm going to tell you more about how we're going to get information about the forest structure. First, we went out and we took time series data. So we went out in the fall and we set up snow monitoring field sites to get information about snow depth over time. And this was a huge effort from many people to go out and set up these field sites. These are photos from Mark Stone. And we set up time-lapse cameras and snow poles the cheapest way possible to get information of snow depth over time on the ridge. This is set up at 12 sites, 6 on the north, 6 on the south of the ridge. So this is on top of the LiDAR data now. This is just a hillshade. But if you zoom in to our plots, you can see we have 6 on the north, 6 on the south, and they look something like this. They're currently out there right now, hopefully taking snow depth measurements for us. We'll find out when we clean them up. And this is an example of the same density on the south side. So this, we hope, gives us information about snow depth over time at 12 locations. But what we really needed to know was how our forest treatments actually change the forest structure. We have these estimates, of our forest structure with the basal area factor, but it really wasn't quite enough. for us to be able to scientifically evaluate the impact of forest structure on snow. So very fortunate, again, as I've been throughout my PhD, to be able to collaborate with Rapid team here at UW to get snow on LiDAR of our forest post-treatment forest structure. So this effort just happened last week. Yeah, this is recent work, everybody. Right off the press, this photo from Mark Stone of our group and the Rapid team that helped us with this work last week. We had a really excellent time. And what we wanted to do was essentially get snow on information over the ridge and also the change in forest structure. So the flights look something like this. They covered all of our field sites, and it was just really great to learn from everybody. This is the Rapid drones up in the air last week, and we also had ground observations happening. So we were taking field observations for validation data as well. So I've talked to you guys a lot about this problem that I'm still working on solving. So do forest prescriptions for fire resiliency also promote hydrologic resiliency? That's really this overarching idea. And of course, I haven't gotten there yet. This is my general exam. So hopefully, if you guys join me at my defense at some point in the future, then we can answer this question. So that's chapter 3, is a post-treatment forest structure. This will be a manuscript that's currently in data collection, of course, as our sites are out there. But this will be a manuscript that sums up kind of this idea. So I want to wrap this up by saying that, our field site, this field site in Clay Elm Ridge is a really unique opportunity to investigate how these prescriptions impact our snow storage. And the results from chapter 3 will be used to inform forest management in Washington State. Okay, we made it here. It's winter 2023. Last week, we collected our treatment data on Clay Elm Ridge, and we're currently at my PhD general exam. So far, this is going well. So I plan to have 3 more quarters here at UW. I plan to be here through the end of the year. Where in spring, I'm going to submit that first chapter, and we need to go pick up our site. So hopefully we'll have a field day or 2 to go do that. I'm, during that spring quarter, going to be doing analysis on chapter 2 that I've already started. We'll have the summer, hopefully, to take a breath. Fieldwork is complete, and the goal is to really make sure we clean up all that forest treatment data from Clay Elm Ridge. That will inform chapter 3. So yeah, in the fall, the plan is to be working on chapter 3 and put all these things together into my dissertation. But I will hopefully answer these questions that I've proposed to you now. Okay, well, of course, as you guys have already seen, this work has been hugely collaborative. It's so many people involved, the Rapid group and Susan, Emily, and Jessica, who were on the ridge with us last week. And I want to mention that, this project, I got this drone LiDAR data funded because of the mentorship from these other folks. So I worked at the drone lab with Claire Webster and got a lot of excellent information from this SLF group about how to execute these field experiments and this field work. And I had a compliment from Rapid that I knew a lot about drone LiDAR, and they kind of were talking to me about it. And I was like, yeah, it's just because of this other work. I was traveling and I gained a lot of knowledge, and now I'm able to bring it back and use it for our forest management in Washington State. So I think that's really cool. And I'm tremendously grateful for all these people who have been out in the field helping me. Of course, my friends and family too, but you guys will get your love at the end of my defenses. So with that, I want to say thank you, and to my funding sources that have been many. And yeah, if you guys have any questions.
General audience for the next until 10, and then we'll dismiss everybody except for me. If you take their questions after 10, they can ask Cassie all they want then. Stephen is in charge of all the online questions.
Yeah. Awesome. Yeah, for folks online, we'll take questions from the room first, and then I'll move to online. And hopefully, if you want to unmute yourself, we can do that.
Cassie, that was a wonderful job.
Wow.
So thinking about the Cleon site, and you had the figure that showed kind of the temperature compared to the rest of the state, and connecting that with long wave and short wave kind of dominated melt. Kind of thinking of that site and being able to kind of explore aspect and changing temperature with climate change and all that. How, I guess, how much of the state do you think can kind of be represented at that field site? And kind of once you have those before and after and seeing how the snow physics kind of differ, is there a plan to kind of apply it? Because it just seems like such a cool kind of very like applied and helpful right after analysis data set.
Totally. For folks online that may not have heard, there's two parts of the question. The first part is asking about how applicable this is over the state, this field site, and then if the plan is to do management. So yeah, this field site. So as far as the north and south aspects go, it's very unusual for someone to have an entire study site that covers both the north and south aspects. So for us, I mean, that's very unique for a study site, but it's really applicable. I mean, there's ridges that are running in all aspects all over the eastern side of the Cascades that would be in a similar zone to this. In addition, it's not just necessarily the Eastern Cascades, but it's really this wild urban interface where a lot of the management is happening. So it's happening where we want to protect, you know, our residential areas. So it's also just this increase in percentage of it's this lower elevation field site that is on this wild urban interface where management is happening. And so there is a kind of increase in how this would be useful in those zones, especially on the eastern side of the Cascades. So I would say, as far as Washington State, that's how it's useful. And then is there a plan to apply it? I mean, certainly, I mean, so this work is not, you know, this is very different. This is very applied research. You know, a lot of times, especially, you know, you can see in my first two chapters, I'm like being a scientist doing investigative work, and, you know, we're publishing papers and it's really interesting. But this is funded by Washington State Department of Natural Resources and the Nature Conservancy. This work started because they were asking us, hey, we're doing these prescriptions. It is happening. We want to make sure we're also promoting hydrologic resiliency. So the hope is that, you know, since they were the ones really coming to us with these questions, that we can turn in these reports to them, and this can be applied to their management basically as soon as we can have more information. And there's been preliminary kind of work done by Susan and Emily where they're already really strongly in communication about the forest prescriptions that are happening, but the goal would be that it would impact the eastern side of the Cascades, especially in those wild urban interfaces. Yeah.
What's like the magnitude of the signal that you're hoping to see from different forest prescriptions? Like how much longer are you hoping to see snow stick around so that, you know, say that water.
Yeah, the question for people online is, what is the magnitude of the signal for the difference in snow, or what are we expecting? So previous work on the ridge, where Susan and Emily have already done some monitoring before the prescriptions, there was a maximum of 30-day difference in the snow, presence and absence, depending on aspect. So, but about an average of plus or minus 2 weeks is what they were seeing. So, so for the prescriptions, the hope would, you know, since we all have our bias, the hope would be that prescriptions aren't going to have that, you know, aren't going to destroy our hydrologic resiliency. But there could be a chance we see up to a 30-day difference in snow presence or absence, depending on these prescriptions. So the goal would be to really close that gap and to have prescriptions that don't have such a big signal, right? We want to not have such a big swing on the south side and lose all of our snow. So yeah, I would say 2 weeks is a pretty good estimate of a magnitude.
You did such a great job.
Awesome.
Farmers, we're doing that.
Are you seeing a research project out of this? No. The question is if we're in conversation with anyone downstream, essentially, of people that are being impacted by this water. I personally have not been, but I'm sure that other people involved in the work, such as DNR and the Nature Conservancy, they're in communication with people downstream, and I can open it up for you guys if you had any follow-up on that.
Yeah, we work really closely with the economic integrated plan teams. I think at this point, we're tinkering with the whole hydrologic model, if you would say. So it's like one step, and then we have to, run through the whole model to see what did we do, have different things. So we're trying to be very careful not to get some people too excited about what the impact downstream might be. But from that fisheries perspective, fish out migrating the upper reaches of the Yakima area, if they don't make it out of the reservoir, for example, by the end of May, they're dead, or they get plummeted because of the thermal limits downstream. So in all that whole series of sort of dams for the irrigation projects, the water just keeps heating up and heating up and heating up, which changes their metabolism and also the predator's metabolism. And so even if it's not legal limits, they still have to, or they can just be, or they can just hit the limits of this very totally. So the quicker and the colder the water is moving through that system, the more fish you get out. But there's like 98% mortality below Prosser Dam. And so a little bit can actually make a big difference for endangered fish. So that's sort of where my head sits, but I'm a fish person. But I think that's where you'll get more impact as opposed to late season irrigation. I'll stop talking now.
No, it's not though. No, yeah, it's kind of the answer to the question was that there is conversations happening for people online. I'm repeating for you, but there's conversations happening at a smaller scale because really first we want to understand the snow at higher up in the system, so then so that we're not making too big of promises later on downstream. So I think that those conversations could be something to follow up on. Once we understand what's happening higher up, then we can be talking downstream. Yeah. Michelle? I'm very, very fortunate. Thank you. Okay. Yeah. Totally. I think that's perfect. Yeah. Thanks, Michelle. The question is more about the forest prescriptions and if this is representative of what's happening and a little bit more about what is actively happening. So the forest prescriptions, yeah, of course they are actively happening. They're certainly focused on just this urgent impact of saying, okay, well, we want to make sure that we don't have these high severity fires that are coming into our residential areas. So some of it is happening kind of urgency in these interface zones, and some of it happening on a larger scale. So some of it's happening on this like 20-year plan or 10-year plan scale, where Washington State Department of Natural Resources is working to create a management plan for a 20-year outlook of our forests. So there's kind of these two scales. It's of course this urgency where, yeah, we're gonna do management where we can to prevent homes from burning down, but we also want to make a larger plan. So what it looks like in the forest is often we are reducing the amount of fuels that are on the south slopes, so where it's more likely for those fires to spread quickly, and it's happening in these lower elevation areas where there are these interface zones. So it is I don't know more necessarily about the applied prescriptions that are happening, but I think it'd be interesting to find out, and then of course the goal is to really inform this longer plan, to inform this 20-year plan. So, we're not necessarily going to prevent, this is not going to be helping necessarily this fire season that's coming up on us and later in the year, but hopefully this will inform the management of our forests for the 20-year management plan. Yeah. Okay, I think we can turn to an online question. Steve, if you want to ask your question.
It's enough.
Yeah, it's here. You need to unmute. You do. Okay.
Cassie, one thing let's get this blur thing out of the way. No, don't worry about that. One thing that's important on this is you're getting 1 year's worth of very valuable data, which is showing a scenario for whatever's going to happen in 1 year of growth or whatever. And what really matters here is how long does one need to do a follow-up for how many years to see how effective it is. That's one point. That's not your question, but this really matters to your collaborators at the DNR and the Nature Conservancy. And kudos to the supporters of this work. This is hugely important work. So that's sort of an observation. But the other part we need to watch out for, when you commented on the snowpack acting as a reservoir is only useful if it has a very stable result. So if you have a lot of variability, then you've got a problem. So all of this work needs to be tied in with the total Yakima Basin management involving the Yakima Nation and other people as well, which is going to involve how you store some of that water, how you handle the fish downstream and so forth. So this is a part, but you have to recognize that reservoir that you have. And the 5 reservoirs in the basin are very small. They don't add up to much worth at all. They have no real over-year storage capability. So there's buffering that's been built in there that will help, but there's a lot to do that will really matter. But so kudos and kudos and kudos to all the folks who've got behind this, because it really matters what you're doing.
Thank you so much, Steve. Yeah, I just want to mention to the first point that you said about this being a really small region, of course, and it needs to be repeated. Of course, it's 1 year, 1 snow year, which of course that we know from looking at the snow depth in California is not necessarily representative of our entire snow, of what's going on with the snow every year that's changing in the West. So I agree. I think this certainly needs to be something that is monitored long-term. Oh, he's asking about regrowth. Okay. Yeah. So yeah, and if you're also asking, if you're also mentioning about regrowth in the forest too on that type of scale, I mean, at least for this scope of this project, our forest management happened a year ago. So we're in a really good situation where that's not a problem yet. But I think that that's something to consider in the future. There's a few things, we're out in the field and we're thinking about, the forest management is not just impacting the canopy structure, it's impacting the ground as well. We've seen, of course, you have down logs, you have change in a little bit of your ground structure. And then of course, if it regrows, then you're gonna have a change in your forest structure again. So yeah, I think these are all things, excellent things to consider. And outside of the scope of this work, looking at it for multiple years and on the bigger scope of the Yakima River Basin, I think is an excellent comment. Thank you so much, Steve.
We have 1 minute left. One very short.
Well, the main forest metrics, just I was wondering if
Yep, absolutely. Yeah, thanks, Nicoletta. The question is, so thinking more about the analysis, how we're going to quantify the forest metrics, because the important thing here is actually looking at the change in forest structure, of course, with slope and aspects. So, so the plan for looking at the forest structure is, of course, we have gorgeous LiDAR data sets, which give us detailed canopy structure information. But if you're at any point in the ground, of course, like looking up, you'll know that there's a change in your forest structure at any point on the ground, depending on how close you are to a canopy. If you're in a gap, or if you're just standing on the ridge where there's no trees. So our plan is to start looking at, start making classifications for if you're standing on a single point on the ground, how far you are away from a canopy at distance to a canopy at any point. We can use methods such as Julia Mazzotti's 2019 paper to look at the distance from a canopy edge, or other methods to basically determine essentially for any point what your structure, your forest density is, or how close you are to a forest edge. And then we want to do other things such as creating like heat load indexes, such as your 2019 paper. But anyway, so Yeah, but we want to also create like heat load indexes to be looking at the impact of this forest structure and also slope and aspect to understand. So then at every point in the ground for a certain forest structure, we can understand how aspect is going to interplay with that and how slope and.
Let's give Cassie a hand.
Oh yeah, okay. Okay, everybody, we are wrapping up here. Thank you so much for joining in online. And everybody unfortunately needs to leave. And Brittany Johnson, of course, on my committee can stay online. But thank you all for attending. Okay. Break time.
Also good timing. I just reread your 2013 paper yesterday, so it was fresh on the mind.
The picture of the photographer.
Mark is going to be on my paper.